Hello, my name is Cameron Wobus. I'm a senior scientist at Lynker in Boulder, Colorado. Before I get started, I'd like to thank our funding source and my co-authors on this work. This work was funded by the Bristol Bay Regional Seafood Development Authority through a grant to the Nature Conservancy to Lynker. Ryan Spies and Bill Safransky at Lynker were the scientists in charge of most of the modeling work that you'll see here. Dave Albert and James D. Pasquale, both at the Nature Conservancy, assisted with GIS and other tasks. The draft environmental impact statement for the Pebble mine was released in February of 2019. The purpose of an environmental impact statement is to describe the direct, indirect, and cumulative impacts of a proposed project on the environment. Based on our review, the Pebble mine draft EIS dismisses the impacts of a tailings dam failure despite the clear risks to the environment. To fill this gap, we developed a hydrologic model to evaluate the potential impacts of a tailings dam failure on the Bristol Bay watershed. We used software that's been used by the mining industry for similar studies. We developed failure scenarios based on site-specific and historical data, and we used a sensitivity analysis to bracket potential outcomes. In all of the scenarios we evaluated, a tailings dam failure would directly impact hundreds of miles of anadromous waters. A tailings storage facility or tailings impoundment is a large impoundment that holds the waste products from mining. Tailings dams, which hold these tailings back, differ from the water dams that people are familiar with in two important ways. First, they're typically built of earth rather than concrete. And second, they're typically built sequentially so that the tailings will be filled up to a certain level. The dam will then be raised higher than the tailings. The tailings will be filled to that level. The dam will be raised again, and so forth. Because of their earthen structure and the way they're constructed, they fail much more frequently than the water dams that hold back water in reservoirs. Some recent examples include the Brumadinho mine in Brazil in 2019. This dam failure killed as many as 300 people immediately downstream. The Samarco mine in Brazil, not too far away from the Brumadinho mine, failed in 2015. This one was notable in that the tailings that were released traveled more than 600 kilometers downstream and could be seen entering the Atlantic Ocean from space. The Mount Polley mine in British Columbia is notable in that it occurred in British Columbia, which is not by any means a developing country. And yet this dam failed, in part because of engineering failures in that the geology of the site was not adequately understood. The Mount Polley mine's environmental impacts were limited, in part because the tailings that entered the river downstream of the tailings dam traveled only a few kilometers downstream before they entered a large inland fjord called Lake Quesnel. Notably, the Mount Polley Dam in British Columbia was designed by Knight Piésold. Knight Piésold is the same consultant that's been hired by the Pebble Limited Partnership to construct the tailings dam there. The mine as currently proposed for Pebble contains two very large tailings facilities. The bulk tailings facility north, shown on the left, and the potentially acid-generating tailings facility, shown on the right. The bulk tailings facility would hold over 30 billion cubic feet of waste material from the mine, and the potentially acid-generating tailings facility would hold over 7 billion cubic feet of material from the mine. We'll be focusing most of our discussion on the bulk tailings facility north. This is for two reasons. First, the bulk tailings facility north is the larger of the two impoundments, and also is unlined, unlike the potentially acid-generating tailings facility. And second of all, even in the full build-out scenario in which a 78-year mine is proposed, the bulk tailings facility north will be almost identical in both scenarios. One of the notable things about the environmental impact statement for the Pebble mine is that it very clearly states that the dam design for the tailings impoundment is not the safest way of building a tailings dam. These two sentences occur back to back in the environmental impact statement. The first sentence says the following: Dams designed with downstream construction methods are less likely to fail than dams using centerline construction methods, especially under seismic shaking, which is in fact a problem at the Pebble site. The very next sentence says the following: the centerline construction method was selected for the bulk TSF north embankment to limit the footprint and volume of materials required for construction. In other words, the draft environmental impact statement very clearly states that there is a safer way to build a tailings dam than what is being proposed, and that the reason for not using that safer method is to limit the amount of material, which also limits the cost of constructing that tailings dam. The draft environmental impact statement is also quite misleading about the probability of failure of a tailings dam, in my opinion. In the draft environmental impact statement in section 4, it says the following: the probability of a full breach of the bulk or pyritic TSF tailings embankments was assessed to be extremely low. This statement relies on a closed-door workshop that occurred in October of 2018, at which 4 Pebble Limited Partnership representatives were present. In that workshop, they determined the following: a full tailings breach was ruled out as remote during the 20-year operational life due to the likelihood of successful detection and intervention. Based on other statements in the environmental impact statement, the probability of a tailings dam failure is approximately 1 in 2,000 for any given life year of a dam. What that means is that over 20 years, the probability of failure is only approximately 1%. However, what's misleading, in my opinion, about the environmental impact statement is that the tailings dam will need to be on the landscape forever. The tailings dam will not be removed after 20 years, and it will have to hold those tailings back in perpetuity. So if we look at the probability of failure here on the y-axis versus the length of time over which you analyze the probability of failure, it's pretty clear that the longer you wait, the higher the probability of a dam failure. So for example, after 100 years, the probability of failure is approximately 5%. After 200 years, the probability is approximately 10%. And in the limit, if we go all the way out to 2,000 years, the probability of failure is nearly 100%. In addition, the draft environmental impact statement is, in my opinion, a little misleading in that it describes 2 failure scenarios, neither of which represents a full tailings dam failure. So this slide has a lot of information on it, so I'd like to spend a little bit of time explaining what's here. This is a plot of the 28 historical tailings dam failures worldwide for which there's enough information available to determine both the capacity of the dam, which is shown on the x-axis here, and the volume released from the dam after that failure occurred, shown on the y-axis. Based on this compilation of 28 tailings dam failures over recent time, Rico et al. In a 2008 paper determined that there's a nearly linear relationship between the volume of the tailings dam, again on the x-axis, and the volume released, again on the y-axis. Based on that relationship, the Pebble Bulk Tailings Facility North, shown here in green in the upper right, would be expected to release approximately 3.4 times 10 to the 8th, or 342 million cubic meters of tailings. What's described in the environmental impact statement instead is this dot on the lower right-hand corner of the plot here. What's described in the environmental impact statement is a bulk tailings pipeline rupture, in which the pipeline that delivers tailings from the mill to the tailings facility is assumed to break, releasing tailings for approximately 6 hours, after which time that is shut off. The problem with this scenario is that the amount of tailings released from this bulk tailings pipeline rupture is approximately 10,000 times smaller than what would be expected to be released from a tailings dam if the Pebble facility behaves similarly to the 28 previous tailings dams. It's also notable from this plot that the Pebble Bulk Tailings Facility North is approximately an order of magnitude, or 10 times larger than either the Samarco Dam in Brazil or the Mount Poly Dam in British Columbia in terms of its storage capacity. So zooming in now on our study area, based on what we have reviewed from the environmental impact statement, we felt that it was important to look at the possibility of a tailings dam failure to evaluate what its impacts might be on the Bristol Bay watershed. This is a regional view now of the Bristol Bay region, with Lake Iliamna shown over here on the right, Bristol Bay shown over here in the lower left, and this yellow figure up here in the upper right is the bulk tailings facility north. Downstream from the bulk tailings facility, there's approximately 208 river miles until the Nushagak-Mulchatna river system reaches Bristol Bay near Dillingham. Throughout this region, there are also hundreds and hundreds of miles of protected anadromous fish reaches. These blue lines represent the Anadromous Waters Catalog reaches that show where anadromous fish have been documented. The documentation of anadromous fish is certainly not a limitation on where they might be present, and in fact, the Anadromous Waters Catalog itself states that these lines are a significant underestimate of all the stream miles where anadromous fish might reside. I'm going to focus in on two boxes showing our model domain. The first box, shown in yellow, represents the majority of our model simulations, where we looked at tailings dam failures extending to approximately 50 river miles downstream of the tailings dam. Based on those simulations, as I'll show, the majority of the tailings were still moving downstream of that lower limit of the model domain. So we extended the model domain approximately 85 river miles downstream from the tailings impoundment to approximately where the Mulchatna River reaches the Nushagak River. And I'll be showing you simulations that show results from both of those model domains. So first, I'm going to show an animation of what a tailings dam failure might look like in that smaller model domain. What you will see when I start this video is a release of tailings from the north impoundment of the bulk tailings facility here. And these lines here represent approximately how long it takes for the tailings to get to each of these points downstream. These other lines here show the distance downstream from the tailings impoundment in each situation. So we're extending approximately 50 river miles downstream to the end of our model domain, shown here by this black line. What you'll see when the tailings release starts is that they travel downstream and eventually they will hit, in approximately 36 hours, the lower limit of the model domain. When they hit that limit, they will start stacking up on the lower limit of the model. That is an artifact of the model, and in fact, those tailings continue downstream towards the Nushagak. So here's a simulation of what that tailings dam release looks like. The colors shown here represent qualitatively how deep the tailings are at each point in time. They have lots of momentum as they get here to the Swan River, and they start pushing up into that very flat area in the Swan River. And then you'll see them start stacking up on the lower limit of the model domain. So based on this simulation, we determined that we needed to extend the model domain further downstream so that we could see what the fate of these tailings is beyond that 50-mile point. We conducted a number of sensitivity tests on this upper model domain to evaluate how different the environmental impacts might be if different amounts of tailings are released. This slide here shows a sensitivity analysis to the total volume released. In green is shown the 10% breach volume. In other words, this is what it looks like if approximately 10% of the tailings are released from the tailings impoundment. And the orange shows what it looks like if approximately 60% of the tailings are released from the tailings impoundment. Recall from the Rico et al. Relationship that I showed a few slides back that the expected amount to be released is approximately 42% of the tailings. So this shows a low end and a high end around that expected release volume of 42%. In both cases, the tailings are filling the valley sidewalls wall to wall. They're filling the channels in the middle of those valleys. And in both cases, some of those tailings get up the Swan River. The big difference between these two is that the larger breach actually spills over from the South Fork of the Cockatoolie into the North Fork of the Cockatoolie, shown in that orange area at the bottom. And there is much more tailings in the Swan River, shown kind of in the center top of the model. But otherwise, the impacts are largely similar in that the channels and the valleys are both filled with tailings following this release. Based on the simulations from the smaller model domain, even though the tailings are filling the valleys from the South Fork of the Cockatoolie all the way to the Mulchatna River, the majority of the tailings were still passing through the bottom of our model domain. As a result, we extended our model domain down to approximately 80 miles downstream of the tailings impoundment to approximately where the Mulchatna meets the Nushagak. This is a simulation result from the 24-hour breach simulation in which 42% of the tailings are released into the environment. In this case, approximately 45% of the tailings are deposited within the floodplain between the tailings facility and the Nushagak River. Even in this simulation, which goes 80 miles downstream from the tailings impoundment, approximately 55% of the tailings are continuing beyond the lower limit of our model and flowing past the model boundary. Based on the fine-grained nature of this tailings and based on the large volume of water flowing in the Nushagak, is virtually certain that the tailings from a tailings impoundment would reach all the way to Bristol Bay. Based entirely on the results from our 80-mile model domain, in which tailings are simulated to the junction with the Mulchatna and the Nushagak River, the tailings would directly impact more than 219 miles of anadromous waters. These waters are those cataloged in the Anadromous Waters Catalog, which the AWC itself states is a significant underestimate of the number of miles of salmon streams. In other words, many hundreds of miles of salmon habitat would be directly impacted by a tailings dam failure at the bulk tailings facility north. In addition, depending on the copper concentrations in these tailings, which the environmental impact statement states would be approximately 0.01 milligrams per liter, it is possible that those tailings could actually influence anadromous fish behavior such that they may avoid the upper Nushagak River and or the upper Mulchatna River. So even though only 220 miles of anadromous waters are directly impacted, it's possible that large fractions of the Nushagak-Mulchatna River system would also be indirectly affected by a tailings dam failure from the bulk tailings facility north. So I already mentioned some of the potential impacts to the fishery in terms of metals concentrations, but what are the other potential impacts to the fishery? Well, it's been demonstrated multiple times that deposition of fine-grained material in spawning habitat decreases emergence success. Two papers by Chapman in 1988 and Condolf in 2000 both demonstrate that the emergence success of fish from their redds is decreased substantially when fine-grained material is deposited on those gravels. Tailings would act like those same fine-grained materials and could significantly impact survival of fish that are incubating in those gravels. And secondly, leaching of metals from the tailings could create either acute or chronic toxicity to salmonids. The environmental impact statement itself states that water in contact with the tailings is likely to generate acid over timescales of decades, and metals leaching could also be a significant problem if there's a release of tailings to the environment. So based on our simulations of a tailings dam failure at the Pebble mine, it's clear that a tailings dam failure from the bulk tailings facility north would impact hundreds of miles of anadromous waters and potentially impact many hundreds of miles more in the Bristol Bay watershed. So I'd like to leave you with this last quote from the environmental impact statement, which states as follows. The only common factor in all major TSF failures has been human error, including errors in design, construction, operations, maintenance, and regulatory oversight. Based on what I have seen of the environmental impact statement, I believe that the regulatory oversight portion of this human error is one that we should be paying close attention to. In particular, by not looking at the impacts of a tailings dam failure on the Bristol Bay watershed, the EIS as currently written avoids one of the most significant potential impacts that this mine could have on the environment and the Bristol Bay fishery. So I'll leave you with that, and if there are any questions, please feel free to contact me, Ryan, or Bill Safransky at the emails shown here. Thank you.